All right, and now everyone is ready to head into the last concept in terms of finding maximum and minimum values. So now allow me to introduce a term here that's called absolute maximum, and as well as absolute minimum. Okay, and so again, as I said earlier, these shorthand writing is for maximum, MAX is for maximum, and MIN is for minimum. So the idea now is briefly as a graphical explanation. Then, so now we have been learning up to this point those up and downs here where we have horizontal tangent. We refer to those as a local maximum, and here is a local minimum. The reason for that is, again, just briefly, that it's a maximum, but maybe there it's only applicable in its own nearby interval. And then here is a local minimum in a sense that, yes, maybe it's a minimum, but so far what we have learned is it's only a minimum within its own nearby interval. And so now, once everyone is fluent in terms of how to find and detect all of the local or relative maximum and minimum, then we are ready for nailing down what it means by being an absolute maximum and absolute minimum. So as the term itself being written in red right here, absolute maximum and absolute minimums, it now refers to, because now another point I could have also explained, and you have seen it already, that when you're looking at local maximum, there could be multiple peaks like that. So there could be more than one local maximum that can happen. Okay, so there could be more than one local maximum. But so the idea of absolute maximum now is that among all the up and downs and all the up and downs, at least what naturally making sense now is that which one is absolutely the highest one. Or among all the local minimums here, at least what's naturally making sense for us now is which one among the peaks here is the absolutely lowest. But I'm just saying that that's the easiest way to think, but that's not all it means by being an absolute maximum or absolute minimum. Okay, so be careful. I'm later on going to add in some more details for that. But that's basically the idea right here, because see, again, the limitations with finding all of these local minimums and local maximum is that it's only maximum in a certain local area around it being maximum, but now throughout the entire graph, where is the absolutely highest value, or throughout the entire graph, where is the absolutely lowest value. And that's that's what we're heading into. We're looking for, we're tracking down where is the absolute maximum and where is the absolute minimum. Okay? And so now I am going to introduce, as a written version on the board right here, as a written definition on the board. All right, so as a definition on the board right here, then I am going to say a value f at c, okay, is an absolute maximum of f of x. Okay. If, so now the requirement here that needs to be satisfied here, if the function, so just very similar to what we have seen back in when we were studying the local maximum minimum. So if f of x, the function value, is less than or equal this value f of c, okay, then that's, but then here I have to add in a requirement for all x value in the domain, okay, in the domain of f of x. Okay, and that's what it means by being an absolute maximum. So absolute maximum, so if this guy, we call this value the highest one, if anywhere else of that in the entire domain. So now be careful with this term entire domain right here. So now you got to know that some function has infinite domain, so it can run infinitely, horizontally expand to the left infinitely, and it can horizontally expand to the, infinitely to the right hand side. So it can have an infinite domain like this, but there is a way to find out, so absolute maximum here means in the entire domain. Okay, then where is the absolutely highest point there? And that's what it means by looking for an absolute. That's how we define an absolute maximum value. Okay, and so in that same way, now I am going to modify this definition of mine to get into what it means by being an absolute minimum value. So a value f of c is an absolute minimum if the function value is always above that f of c value, or at least equal to, and that's why we call it the least, the minimum, the least value. So if f of x is greater than or equal to f of c for all values of x in the domain of the function. So just like that, we can have a function that has an infinite domain like this. But then if there's a point x equals c where throughout the entire domain this is the only lowest value, or this is the lowest value it can get, nowhere lower, then that point here is called an absolute minimum. Okay, and so just like that, now we are heading into finding an actual example, looking at some examples of where we are finding absolute value, absolute minimum, and absolute maximum. All right, so now let's look into example 5 right here. So I want to find the absolute maximum. Okay, or let's say I want to find all absolute minimum and absolute maximum and absolute minimum. Values, okay, of, all right, and so now here's the thing. So as just right out from the definition, then I said, it's, if we're looking for an absolute maximum, then it's the value f of c where the function is always, if this is a maximum, then the function f of x in general has to be less than or equal to f of c in, this is what's dangerous right here, in the domain, okay, in the domain of f of x. Okay, so by default, a lot of time by default, it takes us back to the idea of finding the domain, but a lot of times function has any function comes with a default domain where it's just either like a whole real values, like a whole real line, a whole line of real values, which extends infinitely, all the way from to the infinite negative infinity to all the way to negative infinity to positive infinity. But in other cases, sometimes the function can also have a restricted domain where it's, instead of taking the entire line of real values, we can only restrict a function down to a certain given interval like this. I mean, there are applications out there where our function is only defined on a certain interval, and that's all it needs right there. So we can, this is what's so-called, we have a finite domain, a domain where it is a finite interval right here. So the easier case now, so I'm trying to explain about that domain. So the easier case now, let's look at the kind of problem where we are going to find an absolute maximum and absolute minimum, where our function here is, okay, so we have a function f of x equals x to the fourth minus 2, and I mean 8 x squared plus 16. So now I'm going to clarify what I was saying again. This function itself is a polynomial. Just by default, it should be able to have an entire domain, whatever length these things going on. And I don't mean to really, we don't have to draw the graph, but it being a polynomial, any polynomial has the domain being, the actual domain is negative infinity to infinity. That's the actual domain of this function. But now, I want to, in this part A of our example, instead of getting into the entire real domains, the entire domain being the whole real line here, I am going to ask, or to work on this function, find the absolute maximum, and absolute minimum values, but only on this restricted domain. It's a finite interval from -1 to 3 right here, because this is the easier case. So that's the thing I want to give a sort of like a friendly warning for anyone about getting into doing the kind of absolute maximum and minimum values problem. It really depends on your domain as well. Either you are having a finite domain like this, which is the easier kind of problem, or you're going to be running into the actual domain where it runs into like a whole infinite line of values like that. Okay, so now we have a domain like this, being a finite interval from -1 to 3, and it's an inclusive closed interval. Okay, and so now the first step, and in the way how I was explaining earlier, when we are about to detect absolute maximum and absolute minimum, now it's all about we have to first track down all of those turning points, those peaks. Maybe your interval is somewhere from A to B here. Maybe you're in a restricted interval, but you have to detect all of the turning points existing inside of your interval first. Okay, so maybe inside of your intervals we're gonna have to recognize a few turning points, and also we need to consider those 2 points that happens right on the two ends, the left end and the right end. That's the plan of the problem right there. Okay, and so now as you can see in my brief planning right there, see, we want to track down all the turning points. And so these turning points, again, in earlier terms we have learned, these are the critical values that exist inside of the interval. And hopefully you picked up my wording clearly. We want to find all the turning points, all the critical values existing inside of your given interval. And then after finding all of those, yes, we're going to go ahead and determine if they are local maximum or local minimum. But then we also need to consider those points that happen right at the left end of the interval and the right end of the interval. Okay, so that's the plan right there. And so now in that way that I'm saying, this is how we are getting into real work right here. So to find all of the local maximum and minimum, or all of those critical values, yes, first thing we need is to find our derivative. Okay, so our derivative easily comes out to be 4x cubed minus 16x, and that term being a constant is going to become a 0. So our derivative here, f prime of x, is simply 4x cubed minus 16x. So we have our first derivative. Okay, and so now, so from that point on, I am going to head forward and set my derivative 4x cubed minus 16x to equal 0, because we want to find all the critical values. And so now we want to solve this equation for x. That's what we're doing. So this equation came out from setting that our first derivative to equal 0, and that's like the standard step right there. First stage of getting into any of these problems. Okay, so now I am going to solve this. It's easier to solve this equation here by factoring. So I have a common factor for x here throughout all the two terms on the left-hand side. So I'm factoring out 4x. My inside of parentheses here gives me x squared minus 4 and equals 0. Okay, and so I can factor further that x squared minus 4 into two other complete factors, two other complete linear factors. So now on my other board, my equation becomes 4x as one factor, but then two other pairs of parentheses, x minus 2 and x plus 2, okay, equals 0. Okay, and so now as far as critical values, we are so close of finding it. One of them is x equals 0. That came out from setting this 4x equals 0. So setting 4x equals 0, we can solve for that and get x equals 0. And then we are going to have another one. Setting x minus 2 equals 0, we are going to get x equals 2. That solves our equation. And just like the algebra that we've been doing, setting x plus 2 to equal 0, we are going to solve for another critical value, x equals minus 2. So now we have found 3 solutions to this equation. And now these 3 solutions to this equation now are being referred to as, these are our critical values. Those are the critical values. Okay? But now, so just like the earlier example, we are on our way to first find all the relative maximum and relative minimum. But this time we have to be a little cautious that before we construct the sign chart, because that's our thing we're heading out for next. But before we constructing the sign chart, we have to ensure the critical values we found, or in other words, we have to ensure that we're only working with the critical values that falling inside of this interval. Okay? We only need to consider, we only need to look at those, work with those critical values that are being inside of this interval. And so now our interval here, our finite interval here is saying that we're looking at anywhere from -1 to 3 for x values. So that means as far as the actual critical values, we found 3. We found x equals 0, x equals 2, and x equals -2. But we are going to disregard this one because it's this one here as far as the interval given for our function. So our function here, in other words, our function here has a limited domain. So this is the domain we want to work on this particular function. Even though it's not the real, true, actual domain of this function, but the way how this problem gives us, we're only interested in working on this limited, restricted domain. And so in that domain, we only need to be concerned about those critical values happening inside of our given finite domain, like that finite interval. And so in that way, now hopefully I'm clear about why we're ruling out, right, disregarding that critical value. So in other words, inside of the domain given here, we only look at these 2. So these are the one that's being in -1, 3 in that domain. And so now I am going to construct a table of values only based on these 2 critical values. Okay? And so now I must erase part of my board here to get ready for the sign chart. So when it comes to the sign chart step, all right, so here's my line of values. My line of number 0 can be a value somewhere here, and 2 is another value to the right-hand side. So we have to put all the critical values in increasing order from the left to the right-hand side. And now I am going to, just like the earlier example, I am going to produce a row below to investigate the sign behavior of our f prime. Okay, and I am going to produce another row below right here to investigate the increasing or decreasing nature of our function. Okay, and so now this interval is the interval of all the x values being less than 0, but of course being anywhere from -1. Okay, and then this interval here is anywhere between 2 and 0. And this interval here is, of course, anywhere above 2. but see, above 2, but we stopped at 3 right here. So it shouldn't really matter too much about that. So now I am going to pick a value. So I'm going to, in my mind, for simplicity, I am picking up -1. I'm testing at a value x equals -1. You can still pick values outside of the given interval as well, because I mean outside of the -1, 3 interval, as long as right now we're aiming at the sign chart. So other viewers, if you are picking values at the other outside of this interval, that's okay, as long as you are, right now we're inside of the interval between 0 and -2 for this. This column right here is basically indicating between 0 and -2, okay? And so as long as you pick a value between 0 and -2, even though we're only allowed it up to -1 right here, but it's still okay. So I pick -1. -2 works the same way. We are going to substitute this value, f prime at -1, right, into our derivative. And our derivative was 4 times x cubed. So now x cubed is a -1 all cubed minus 16 times x, which is -1 substituted in. So in that way, my value, and I don't think I need to step out for the calculation here, this is going to be a -4 and plus 16, so I'm looking at a positive 12 right here. Okay, it's a positive 12. So my that means my derivative in this interval is going to be a positive sign. And I should have emphasized that it was a positive answer, because the value is not what I need. What I need is a sign right here. So in the interval less than, so less than 0, okay, and between, even though, like I said again, even though we are only allowed to anywhere from -1 to 3 for the entire domain right here, and I picked -1. You can pick other value right there, but our value, for my value that I chose, it's positive 12. So at least in the entire interval here from -1 to 0, our f prime is having a final output sign being positive. So now let's move on to the next interval. So the next interval now is going to be between 0 and 2. So now I'm going to pick x equals 1, for example. You can pick 1.5, you can pick another one like 0.5 or something like that, but I understand that it's very easy to go with the whole value. It's better that way. So substituting x equals 1 into our f prime. Our f prime is 4 times x cubed, which is substituted by 1, minus 16 times x, which is substituted by 1. So here I'm looking at 12, but negative. Okay, so it's negative 12 going in this for this particular interval. And so that means my f prime is going to have a negative sign in the entire interval between 0 and 2. Okay, and so now for the next interval, for x being greater than 2, okay, but like I said again, we are ending our domain at 3, so it's better that we just choose an x value that's anywhere. How about, let me remodify my interval here a little bit, anywhere greater than 2, but we can pick value up to as large as 3. Okay, anyone choosing a little bit above 3 is also okay, because in the end this last interval is all of those x values above 2. Okay, so I stop at 3 simply because the problem gave us the interval that ends at 3. So for safety, then we pick a value that only ends at 3 right here, and that's why I also chose a value that safely ends at -1 here on the left end. But this interval, like I said, is actually a little longer than that. It's actually anywhere between -2 and 0, because remember the other values that we ruled out simply because it's not inside of this interval from -1 to 3. So now I'm picking x equals how about 3? Perfect, because we do stop at 3, but we do allow value to equal 3. Okay, so now in that way, I am going to substitute f prime at 3. substitute 3 into our f prime. So our f prime says 4 times x, which is substituted by 3x cubed minus, and now 16 times 3, right there. Okay, and so now so my calculation turned out to be positive 60. Okay, so I quickly test for the sign of my f prime in this interval, and I found out that it was a positive sign. So I'm not too worried about the value itself. This sign right here is what matters for us. Okay, so now looking at, now we completed our sign chart for f prime right here. Then that means the function in this interval anywhere from -1, right, and before 0 over here, then our function will be increasing in that interval, and I'm even, see, that's increasing. And over time, over my years teaching, I eventually prefer using the arrow indication rather than writing increasing or decreasing. But see, from the left to the right, my arrow notation is pointing higher from the left to the right. Okay, and so for my next one, in between this interval between 0 and 2, then my function is decreasing due to the negative sign of our first derivative. Okay, the function is decreasing. And in the next interval over, our function is increasing. Okay, due to the sign of our first derivative being positive in that interval, so the function is decreasing. And so now we have enough conclusion as far as the local maximum and the local minimum, just like how we did that in the earlier examples. So this point right here, the function rises to a peak and then turning its way down, so that point must be a high peak. So this is now a local, okay, maximum, or a relative maximum. That's another way of saying that. And this other point here, look at the way, observe the way how the function is behaving. The function itself is dropping, but drop to a certain low and then hits back up. So this point right here at this critical value, I could have also highlight those two values to make it a little stand out. These are, this point right here is a local minimum. So we're having a local minimum. So now, so we have now found our local maximum and our local minimum, and these are all that happens. These are all that happens inside of our given interval between -1 and 3. And I mean anywhere from -1 and 3. Those are all that happens right now. So now I'm ready to put in. So here's the, but notice again, ultimately we are not looking for, see, the problem did not ask anywhere for local maximum and minimum. So we found, yes, we found local maximum and minimum, but we have to use that for the next step. So we're not going to stop at finding out the local maximum and minimum. This is what we do next. So now the function itself, I am going to substitute in x equals 0. So recall that this is where we have a local maximum, where we had our local maximum inside of this interval. So f of 0, I'm plugging that critical value into the original function. And now I'm looking at 0 to the 4th power minus 8 times 0 square plus 16. My final value comes out to be 16. So at this local maximum, our function, our function hits to as high as positive 16. Okay, so that's how high the function hits at the local maximum. But I also need to find out how low our function hits. So at the local minimum. So f of 2 right here, I'm looking at 2 to the 4th minus 8 times 2 square plus 16. All right, and so that's a 32 right here. That's also another 32. So my function here hits down to a 0 right there. All right, and so now at this other critical value inside of our interval here, we've reached to so far a local minimum, and this local minimum hits to as low as 0. Okay, but now, as I said earlier, recall that I put on a picture earlier that, hey, inside an interval inside an interval from a to b, right? You can have a function up and down like this. Okay? And so maybe you have a local maximum here, a local maximum there, a local minimum here. So we already have found all the local maximum, all the local up and downs inside of the interval. But now we also need to consider the endpoints. Okay? We also need to consider how high the value hits at those two endpoints. Okay, and so now that means we're only about 75% done for the problem. So now I'm going to use the term about left on the left end here, or left end point. So on left end on this interval, the left end is x equals -1. I am going to substitute the left end into the function as well. So f at -1. Okay, f at -1. It gives me -1 all to the 4th power minus 8 times -1 square, okay, and plus a 16. All right, and so now that gives me a 9 right there. Okay, it gives me a 9. And so on my left end, I hit to as high as 9. My value came to as high as f of -1 equals 9. All right. So now I am going to also substitute my right end into the function, into the original function. And now I need to move on to my other board right there and erase out the sign chart here. So now on my right end of the function, then I am going to substitute in x equals 3, the right end of my interval right here, into the original function, not the f prime. Okay, so substituting x equals 3 into the function, I'm looking at 3 to the 4th power minus 8 times 3 squared and plus 16. Okay, and so we are now looking at positive 25 right here, positive 25. And so now we have 5 different values. So I need to really switch back and forth between the two screens right here. So this is what it says in our graphs, or this is what it says in our function. At the left end, when x equals -1, we are at the outputs being as high as 9. Okay, and then when at x equals 0, we hit to as high as 16 for a local maximum. And when x equals to 2, we hit to down to as low as 0. And when x equals to 3 right here, we hit to as high as positive 25. So now, here's how it comes to the final answer. As far as absolute maximum, we just simply need to find out, hey, among all of these output values right here, which one is the highest one? Which one is the highest value? Because we're looking for absolute maximum inside of the given interval. So that means what? We have our function, our absolute max. Another way of expressing your answer here. That's happening at, see, f of 3 right here equals 25 here. Yes, and it's happening at x equals 3. And many textbooks also just write only that's one line right there. This is our highest value, our absolute maximum in this interval at x equals 3. That should be enough, but I'm just a little over careful. And so now, absolute minimum. We just now simply look for the lowest one, the lowest candidates among all of these. So, okay, we got 5 candidates. There's the right end, there is the left end being at 9, there is a local minimum, there's a local maximum. We actually only had 4 candidates right there. So now you can tell the one that wins the lowest absolute minimum has to be at our local minimum as well. So that's why it makes sense that we have to start out finding and detecting all the local maximum and local minimum as well, because those can also be qualifying candidates. I'm using that term, qualifying candidates, for being the eventual absolute maximum or absolute minimum as well. Okay, so now f at 0, it was our local minimum, but now it's also our absolute maximum. Absolute minimum in this restricted interval. I'm looking at the wrong critical value. So we hit down to as low as 0, but it was at x equals 2. Okay, so at x equals 2. That's how we found the absolute maximum and the absolute minimum of our function. Okay, and now before heading out to the next example, allow me to take a moment to erase the board here. And now I'm going to write down a generality of how we carry out a problem that finds an absolute maximum and absolute minimum. So for absolute maximum and absolute minimum, this is how we find them. So of course this is in a domain, so it could be an infinite domain or it could be a restricted domain, but the first step right here is to find I'm going to find all local, or how about to be a little more precise, I'm going to find all critical values. Okay. Actually, it's better to say the local, I'm going to find all the local maximum and the local minimum. Okay. Inside how about the highlighted term here, the given domain. So now what I mean is, the given domain might not be exactly the actual domain of a function, because a given domain could be sometimes just a restricted domain as being reflected in this problem right here. So now inside of the given domain, we're just going to have to find all local maximum and all local minimum. And the work might involve ruling out some local maximum or some critical values that outside of the given domain. So we only have to worry about what's happening inside of our given domain. And then once we found all local maximum, minimum inside of the local domains in terms of how high, how low the hits right here, the next step is also to consider, okay, so find left end, okay, and the right end. Right? We have to find those two as well, because a lot of time for a left end and for a given domain, we're going to have a definite left end and a right end. We're going to have to also find the values, right? So to be precise, let's say we're going to find values at left end, okay, and right end. That's a little better a little more precise to say right here. We're going to find the actual values at the left end and at the right end. And now at the last step here is we're just going to simply compare among all these candidates right here. Okay. So the highest value, okay, is the absolute maximum. Okay, and the lowest value, okay, is the absolute minimum. All right, and that's how it is. to find absolute maximum and absolute minimum. And so the good news is that it's more commonly to have a problem for us to find absolute maximum and minimum with a given restricted domain like this. But there could be times where the problem becomes more challenging. There will be times it's not as oftenly, it's not happening as frequently as this problem where we have a given domain. So the problem on a given domain is easier for us to find the left endpoint and the right endpoint. But I'm not saying that it's only the kind of problem where we have a given domain like right here. Sometimes the given domain is the entire infinite domain. So let's look into another example where it's slightly more complicated, slightly more challenging, okay? So now I'm going to call that example part B. All right. So this example part B right here, same function. Anyone viewing my video at this point is probably feeling a little shocked that I'm using the exact same function. But for this problem, my plan is I'm taking away that given interval. So we don't have the interval. That means by default, the domain here, the domain of a function like this, being a polynomial, is the entire interval from negative infinity to infinity. Or it's a line of, back in my days when I was learning calculus, when I was learning math, a lot of time my professor was saying it's just all values of x in the real numbers. That's another way of expressing the domain right here. But now in these nowadays in these textbooks, now I see that a lot of time textbooks authors put the domain as an infinite domain like this in the entire line of real numbers as an interval from negative infinity to infinity. So whichever way, it's just a different ways of writing it. Okay, but so now that's just an even worse thing is that the even worse thing is it's not even indicated. You just have to automatically understand that when you have a function just given and then without any clear indication about the domain, being a polynomial like this one, you got to know that it has an infinite domain like that. So the domain here is all real values, all the x values in the real numbers from negative infinity to infinity. Okay, and that's the whole reason now I'm looking for absolute maximum and absolute minimum in the infinite domain of this function right here. Okay, and so I'm reusing this so that we don't have to waste all of our efforts finding the critical values from the previous problem. And so now I'm just gonna restate. We don't have to restart all of that. We don't have to reinvent the entire wheel for all the finding the critical values because we have already found them. So the critical values here we found were 0. Is this in the domain? Yes. We found another one, x equals 2. Is this in the domain? Yes. With this new domain here, just recover yourself here in the new function. I took away that restricted interval. So that means the real domain of this thing is the whole line of real values. And so that means we also going to take the other critical values we have found in the previous problem in part A. Okay, so now this time we're going to take all three of them. Okay, and so now that's the one. So I'm going to go ahead and move on to the board, and I hope when I wrote down my other board earlier about a general guidelines for how to find absolute maximum and absolute minimum, then anyone has already had enough opportunity to take notes, or feel free to pause the video and take notes if you have to. Okay. But now, assuming you already had that all written down right here, I am going to erase this. And let's move on. All right, so now as far as the sign chart and to maximize my board space, I'm not even going to write down the title of the sign chart. It's just a sign chart. So now putting all three, because this time we're taking all three critical values we've had. And so the sign chart is going to look as following on the line of real values. Negative 2 is the one on the far left here, is all the way on the left. And we have a 0, okay, and we have a 2 here. So we got three separate intervals. And then this interval here is for all the values of x less than negative 2. this interval here is for x anywhere between -2 and 0. Okay, so these are our critical values. Allow me to put them in circle like that, so that they can stand a little more, stands out. Okay, so, and this is between 0 and 2. All right, so now I'm going to again consider the sign behavior of my f prime. So my f prime here, f prime of x in this interval. So now let's pick a value less than -2. And this is probably the only thing the extra compared to the earlier example, because you see this one right here I already picked. For this interval I already picked x equals -1 in the earlier example. So you can recall the result from the earlier example. And then I already picked x equals +1 in this one right here. Okay, and that all worked. Okay, and I have already picked this last interval is x greater than 2, and I have already picked x equals 3. So we can completely reuse all of these information, all of the 3 information here from the earlier example. The only thing we have to do a little bit of work here is this very left-hand side interval, which is a little extra compared to the earlier problem. So now here I'm going to pick x equals -3. How's that? Okay, it's in an interval that's less than -2. All right, so now we are going to substitute f at x equals -3 into our f prime right here. So recall that our f prime was f of x equals 4x cubed minus 16x. And so that means f prime at -3 is going to give me 4 times -3 cubed minus 16 times -3. So my calculation came out being -60. Okay, and so now, so for other viewers who picked a different values, as long as your value was in this interval over here, then this is the sign you should be also expecting. And so this tells me that my interval, my f prime, will come out with a final sign being negative in that interval for x less than -2. And then now we can recall from the earlier problem that this interval was positive, and this interval here was negative for f prime, and this last interval was positive. Okay, and so now as far as the sign of our f prime, we're done. And let's use that to decide our increasing and decreasing nature, our behavior of the actual function. So now the function here is going to be decreasing in that interval for x less than -2, decreasing due to the negative sign of our f prime. Okay, and then the function will be hitting to a low and hits back up, so increasing in that interval as we have seen earlier in the earlier example. So there's a decreasing interval here, there's an increasing interval there, there's a decreasing interval right here between 0 and 2, and our interval from 2, between 2 and positive infinity is another increasing interval. And so now this sign chart here is now telling me that on these 3 critical values, here I have a local minimum, because the function was dropping down to a low and hits back up. This point here is a local maximum, because it rises up and hits to a stop and make its way back down. So it has to be a local maximum right here. And so this sign chart only tells you about local maximum or local minimum. And then same way here, same argument here, I can call this a local minimum. I can decide that we must have a local minimum at x equals 2. Okay, so these are what's going on at these critical values like that. So now I am going to proceed into doing the actual calculation. So let me step back on my other board like that. All right, so now I'm going to clear out this information. So now f at -2, I am going to substitute our first critical value into the original function. and we're looking at negative 2 to the fourth minus 8 times negative 2 square plus 16. Okay, and now we really are going to find out how low that, because at negative 2 we already decided from the sign chart that we're going to have a local minimum here. So the value here, whatever that is, it's going to be how low it hits. Okay, and so in my calculation, all right, so my calculation shows 0 here. So for this local minimum, we hits down to as low as 0. Okay, and so now the next one here is going to be f at 0. Okay, so that was 0 to the fourth minus 8 times 0 square plus 16. And we already knew, I mean, we can easily calculate that this is 16, just like how we've had in the earlier problem in the example. And now we have another one here. So f at 2. And then now it's going to be 2 to the fourth minus 8 times 2 square plus 16. All right, and again, from previous problem of the same example here that we found out that we already had, it's down to 0 here. So local minimum, local maximum here. But now, so these are all the local maximum and minimums that's happening inside of our, I mean, in the entire domain, in our given domain, which is in this case the entire line of real values. So what about left end and right end? Okay, so keep in mind, any function has left end and right end, but what matters whether it is a definite point or an infinite, or you know, an infinite point or something like that. So now we have to find out right here. So we're still going to have left end and right end, but and observe how I'm moving on with this problem. I'm progressing on with this problem completely without looking at the graphs, because I'm assuming that, allow me to assume that not everybody is using a calculator in these days. I mean, even surprisingly, not everybody is that comfortable with a calculator. So that's why I'm assuming that I'm showing the kind of technique, the trick where you can work it out completely without worrying about having a graphing calculator. Because we don't even know how to graph by hand. We're not patient enough to graph these things by hand. Okay, but now my main aim is to find out what's happening on the left end and what's happening on the right end. But left end and right end might not be a finite point, because we don't have an interval like this. We don't have a comma b. We don't have things like that so that we can easily plug it in. We don't have a finite interval given here as a given domain. And so that's why in this case right here, let me recall an old concept we have already gone over long ago. Okay, so for this problem, how about for a left end? In the end, if left end is not a finite point, is not a finite calculatable point, then I'm going to consider the left end as a left end behavior. Okay, left hand behavior. Does that recall some concepts we have learned a little while ago? Left hand behavior is another way of saying we're going to find the limit of our function as we're letting x approaching negative infinity. Okay, and so that is another way of saying it's a left hand behavior. And so now that means we're considering for x cubed minus 8x squared plus 16, taking that limit as x going to negative infinity. But now it seems like I have to bring back a lot of old stuff, like a lot of past material to understand, but really it's not that bad. Our function, and I noticed I wrote down the wrong power here. The power does make a lot of difference. It shouldn't be 4x, it's x to the fourth. Okay, it shouldn't be 4x cubed, so x to the fourth. But what I see here is I'm looking at a polynomial. And with this polynomial, this is even degree, okay, and it's also having a positive coefficient, even degree, and see the coefficient in front here is we're looking at a positive lead coefficient. So that is enough for me to say that on my left end, my function, whichever the graph is doing in the middle, but my left end has to point up like that. Okay, and my right end is also going to point up like that. It's the way how we're looking at polynomial. In this case, you're having an even degree and with a positive leading coefficient. So now I can say that this left end here will be rising to, according to the picture I was drawing, then my left end will rise to positive infinity. Okay, rising to positive infinity. And now I'm gonna put a pause on that, and let's now look over to our right end. And now same way, right end behavior. Same function of ours right here, x to the fourth minus 8x squared plus 16. Now I'm going to consider x approaching positive infinity for f of x. And this is taking limit as of the function x to the fourth minus 8x squared plus 16. Okay. And x going to positive infinity. Okay. And this one right here, as I drew in the quick picture earlier, then even degree with positive leading coefficient, the right end is also going to rise like this, okay, for the right end. And so in that way, I am also going to get a positive infinity, okay. So that means on the two ends, the function is just going to keep rising, unlimited, rising, unlimited, okay. So that means now we are ready to make our final conclusion in terms of finding the absolute maximum and absolute minimum and all that. So now putting all the pieces together. Yes, as far as low, we hit down to these two are being the lowest. These are the qualifying candidates for being the lowest, because the function does not get anywhere lower. Because think about it. On the two left ends, we don't have to worry. On the two ends right here, left end and right end, we don't have to worry because they keep rising to positive. See, positive infinity. That means the function keep blowing up like this, unboundedly. Okay, but among all of those values, then it looks like 0 here is the lowest value the function can hit. And so now my conclusion says we have our absolute for absolute minimum. We have found f at negative 2 equals 0, and f at positive 2 equals 0. So these are the value, how low that is, and that's happening at these 2 points. They're happening at these 2 points. X equals x equals negative 2, and at x equals positive 2. So we have to notice that the way how it is, then when it comes to absolute minimum or absolute maximum, there can only be one value for how low it is. So, but it could happen at multiple places. Okay, and so now for absolute minimums, it reached to the lowest vertical value is 0, but it happens at 2 different places. Okay, so we found the absolute minimum. But now, what about the absolute maximum? Again, this thing here, this value y equals 16, the function value f at 0 equals 16 is only a local maximum, but it did not qualify. It did not qualify to be a maximum, an absolute maximum, in a sense that on the two ends it keeps even growing to positive infinity, so eventually it will even exceed 16. Okay, so 16 was a local maximum, but look at the nature of these two, left end and right end. It will even grow higher than 16 eventually. And that's the reason why now I can also ultimately say that for this problem, according to the way how our domain is, then we don't have no absolute maximum. Okay, we do have an absolute minimum. We do have absolute minimum at 2 values, at 2 places, x equals negative 2 and x equals 2. Our function hits down to an absolute minimum. But as far as absolute maximum, we found none, because it's just the way how our function was like that. Okay, and so now for everybody to really understand what's going on with a graph like this, so now I am going to point out the actual graph of our function here. All right, so here we go. Here's my blank screen for here. Okay. All right, so now here's the graph. There's the graph for our function being, let me zoom it out. All right, x to the fourth minus 8x squared plus 16. That's our function. See, so we have three critical values, -2, 0. It was a local minimum. 0, 16. It was a local maximum. And we had another one, 2, 0. Okay, and it was a local minimum. So we had these two local minimums in the beginning. But then now, and when we're putting that in the concept of an infinite domain like this, then only these two local minimums qualified to become absolute minimum. Because see, look at the entire graph itself. It went nowhere lower than 0. Okay, so 0 is the x-axis right here. Y equals 0 is the x-axis right here. So the graph in red right here did not get anywhere lower than that. But it can keep rising higher and higher. And so look at how I was explaining about the left end and the right end. See, left end keep rising up and right end also keep rising up. So even though we had a local maximum right here, but eventually the two ends will exceed that. And that's why this local maximum did not qualify to be an absolute maximum. It only stayed permanently as a local maximum. It was only a maximum in its own area nearby. But these two guys right here, the local minimum, they were local minimums, but now they also qualify to also become the absolute minimum. We got an absolute minimum at x equals -2. Same absolute minimum being 0, but at x equals 2. And that's how we are working on these problems, finding out all the absolute maximum and all the absolute minimum values of a function. And so usually for the students who are outside of calculus, who are about to advance to the higher classes of our calculus, I highly recommend that study carefully this kind of problem where you have a domain, an infinite domain like this problem in part B. But for a bigger majority out there, then we most of the time we will see the kind of problem where it happened in part A, where your given domain is a restricted interval. Okay. All right, so now at this point, before we're completely done with our discussion here and ready to head out to the next lesson, then I would like to make a few clarifications in terms of some common terms, some common terminologies being widely used out there regarding maximum and minimum value problems. So now if we are looking back at that example where we had, so quickly let's just looking back at we did this problem in example 5 right here, and I'm not really gonna look back at the entire example. Let's just look at that function itself right here. F of x equals x to the fourth minus 8x squared plus 16, for example. And let's say we're gonna, and this function here, I'm not gonna worry about the entire domain of that function, but we have seen through example 5 that so here we're not really looking at the entire example 5, but we're looking at specifically at that function in example 5. Okay, or you can see itself as just simply as a function. And so this function during our work right here, we have already found that as far as absolute minimum, just as far as the absolute minimum, and as well as the local minimum. Okay, then it happens at you see it came down to the value being f of -2, and that was 0, and f of 2 also equal to 0. So we have a minimum. Okay, and so my point is minimum or maximum can happen at multiple places. So as far as just talking about minimum, see these 2 points are here. Eventually they became the absolute minimum as we have seen in our function. But when we were only looking for local minimums, then it turns out we got 2 bottom peaks, 2 local minimum, 2 different places where we reached local minimums. And so in that way right here, And so the same way how it happens, now I can quickly demonstrate that through a graph. But so the function has ups and down and ups and down. So we can have multiple maximums and multiple minimums, locally or even absolutely. Okay, and so in that way, now I just need to clarify a terminology that if any of you have read any of the standard textbooks for calculus, then we will have a term that says so for, and it's applicable to absolute maximum and absolute maximum, local maximum, or absolute minimum, or absolute or local minimum as well. So as far as looking at minimum, okay, then so really minimum is only if you find one minimum, then that's a minimum. But sometimes when you see the terms minima, okay, that's just a plural. So this just means we have multiple or a plural of minimums. That's it. So multiple of, or minimum in multiple places. Okay, so that's the clarification I would like to make for here, in case there has been any or there's been any confusion when you're reading the textbook for here. And so that same way for here. So now maximum is at one place. Okay, but you will somewhere here and there hear the term or read the term throughout textbook that say maxima. Okay, then this term right here is referred to, we're looking at maximum. Our function is reaching maximum, okay, in multiple places. All right, so that's some clarifications about the terminologies that you might run into somewhere here and there throughout different textbooks. And so now maximum, minimum or maximum, in the end, any of these, they're indicating a certain level of being extreme. Okay, so being minimum means we're at the extreme of low, and being a maximum means we're at the extreme of high. And so in that way, either being a minimum or being a maximum, then we refer to this as any of the maximum or minimum is an extremum. Okay, and you will also see this term somewhere here and there throughout different textbooks like that. Okay, so an extremum is basically either a maximum, a minimum, or a maximum. Any one of that is an extremum. So once again, singular, it's an extremum because maybe we recognize a maximum or a minimum at one single place. But then extremum can happen at many or multiple places. So again, in plural. Okay, in plural, then we're looking at extrema. Okay, so those are the terminologies that I would like to point out. So, and there are a couple other terms that after this I'm going to head into. So once again, extrema means we can have multiple peaks, high peaks, local maximum, local minimums, and local maximum, and other local minimums, and all of those together we're looking at extrema. Okay, and so now the whole purpose of doing any of these, and the whole purpose of learning in depth with all of these techniques, because the ability to find maximum and minimum value is going to become extremely useful for you when we're actually running into doing some actual application problem. So I will be offering the different video lessons on how to apply your understanding in finding maximum and minimum values in application problems separately in different videos. But now, before you start looking over to those videos where we learn how to apply our skill in finding maximum and minimum values of problem, there are a couple of terminologies to get yourself prepared for that as well. So again, if we're looking at any function, okay, and let's say I just stay back with that same function again, x to the fourth minus 8x squared plus 16, any function. So any function we can come up with maximum and minimum value. And so when we are in the work of finding, if you are asked to find, okay, extrema. Okay, so now I'm starting to use that general term right here. When we're asked to find extrema of f of x, for example. Okay, so when we are in that situation where we're finding extrema of f of x, that means now you know we're finding maximum and minimums, and it could happen in multiple places. Then if we're doing that kind of work, then our function here, okay, our function f of x, it's our target to be able to find, it's our target so that we can find where the maximum is and where we can hit the minimum. And so f of x is being regarded as, when we're actually doing an applied problem, then f of x is being regarded as the objective function. Okay, we have an objective function right here, because for that objective, our goal is to find where it gets best, highest value, or find where it gets lowest, and how high is the highest and how low is the lowest. Okay, and so the function where you are looking for extrema is being regarded as objective function. Okay, and so before any one of you is going to start looking into those video lessons of mine showing how we can use applications, and I have to also admit ahead of time that there will be no instructors out there able to give all examples of how we find maximum and minimum values problems in your applications out there, because this skill, once you've learned, has a limitless amount of applications out there. Where you're an economic expert, you are a scientist, you are a physicist, you are any kind of profession that you're doing, there will be a problem where you need to maximize or minimize finding the maximum value and finding the minimum value in your modeling function. Okay,